Okay, so we're going to begin with volumes by cross sections of known areas. So there's going to be 3 examples total, and we're going to be talking about just squares and rectangles. All right, so a solid is constructed bound by f of x and g of x such that the cross sections are perpendicular to the x-axis, are squares. So if you look in the picture here that I have, these squares, these sides, so imagine like your paper is the graph, all right? And these shapes are standing up in 3D off the paper, and it says they're perpendicular to the x-axis, all right? So here we have curve g of x and f of x. And you know that the area of a square is side times side, or side squared, which is what I have right here, okay? So whenever possible, write what the formula is for the shape that they're talking about, and that'll help you guide you on how to do it. So basically, this is what we have. Imagine these green squares that I have right here are popping up off of the screen. And if we want to write an integral for the total volume, imagine you had an infinite number of these squares stacked so close to each other that they form this solid shape, like the ones that I have in the classroom on the wall. I mean, these are obviously spaced out, but you know, calculus is all about limits. So imagine making these cross sections infinitely skinny. And then when you stack them up right next to each other on the graph, you end up with this solid shape. So we need to find a way to define this vertical distance, okay? Because that is what our side is, right? This right here, this vertical distance. And you know how to find that when we did area between curves. So I need to do the top function minus the bottom function. Now, since these are perpendicular to the x-axis, we need everything in terms of x. If we are finding the volume of a shape perpendicular to the y-axis, everything needs to be in terms of y. So when we still do top minus bottom, right? Top minus bottom. And our top function here is f of x, and our bottom function here is g of x. All right. So if you know that area is equal to side squared, then side times side, if one side is f of x minus g of x, would give you f minus g of x, big parentheses, quantity squared. And then if I were to set up the integral, notice there is no pi here, okay? So pi is just for disks and washers at this point, okay? So don't insert a pi because that's what you're used to. We didn't have pi when we were doing area sandwiched between two curves. We only did it when we were doing volume of solids revolving about an axis or a line, okay? So here it is. Your limits of integration would be in terms of x, okay? And your area, this is your area right here, right? Area is equal to side squared. So then area is equal to f minus g squared, okay? And that's what this is saying right here, okay? All right, so let's move on to another example. Okay, so we have a solid constructed bound by f of x and g of x. This time I've given you the functions. Okay, so the blue graph is radical x, the red graph is y equals x squared, and the cross sections are perpendicular to the x-axis. So that means everything in terms of x. Okay, and they're squares. So we need to, it's just, a lot of these problems ask you to just set up the integral, okay? So I'm not really concerned about you solving the integral. I mean, should you eventually? Yes, but you're not going to be giving anything that's super crazy, okay? So I gave you the intersection points here, but you should still be able to find them algebraically, just in case they don't give you the graph, just in case they don't give you the intersection points. And you know that in order to do that, you set the two equations equal to each other. Okay, I need to get rid of this radical, so I square both sides. The squaring here causes this radical to go away. And over here, this becomes x to the fourth. And then since it's a polynomial, you have to get everything on one side. So I have x to the fourth minus x equals 0. And we solve that by factoring, take out a GCF of x cubed, then we have x minus 1, put them both equal to 0, and those are the x values of your intersection points. I don't need the y values because since this is perpendicular to the x-axis, then all I need for my limits of integration are the x values, okay? So now I need to define, I know that in the area for a square is side squared, so I have this shape right here, and this distance right here, okay, this distance right here is represented by s. And if we do s is equal to top, ooh, I know how to spell top, Jesus Christmas. Let's try it again. Top minus bottom, then our top function is the radical x, and the blue graph, and then my bottom function is x squared. And then you know that the area, since area is equal to side squared, all I did was do side times side, okay? Then we set up our integral. We're integrating from 0 to 1 because those were our x values, the x coordinates for our points of intersection, and there it is.